Last time we concluded the story of the atom with electrons and a nucleus and a discussion of the nature of matter. Now let's look at the nature of space before delving deeper into the atom, because stuff this small and smaller moves so fast that our normal intuition is put to the test, and we have to start to understand some of Einstein's relativity. But before starting relativity, let's take a brief detour back in time to something we think we know, which is, what are Newton's first two laws really? Newton's three laws are commonly taught as something along the lines of 1. An object in motion stays in motion, and an object at rest stays at rest unless acted on by an outside force. 2 is the one commonly known as F equals ma, force is equal to the mass times the acceleration. And 3 is that for every action there is equal and opposite reaction. Of these three, the least attention is usually placed on number 1, since it sounds so obvious, which in its current form is just Newton's second law with F equals 0. However, Newton's first law is far more profound than we're used to. The real form of Newton's first law is in defining inertial frames. The correct way to say the first law sounds something like, an inertial frame is any frame where all objects that feel no force appear to move at constant velocities. The point of this law is not to describe the motion of objects, but to describe a particular type of frame. Only by doing this does the second law have any meaning at all, since F equals ma is only true in inertial frames, as seen in the next experiment. Imagine a ball resting on a table and an astronaut hanging from the ceiling by a rope. Newton's second law tells us that the ball should not accelerate as long as there are no forces on it. Now imagine that the only thing this astronaut is able to see in the entire universe is the ball. He sees no table, no earth, nothing except for the ball. If we cut the rope and the astronaut is in free fall towards the earth, he will see the ball is accelerating towards him, apparently violating Newton's second law, since nothing changed about the ball in terms of what forces act on it. It's still 0, but the ball now seems to accelerate towards the astronaut at 9.8 meters per second squared. How can this be? Well, the astronaut is not an inertial frame. And thus, here we can see why inertial frames are very crucial, because F equals ma only in inertial frames, and the astronaut not being an inertial frame does not observe F equals ma.